Welcome to Lecture 20, 5.2, the addition rule and complements. So our first objective is the addition rule for disjoint events. Alright, by definition, two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive. Exclude. Alright, lots of interesting words here. Okay, so for example 1, we're going to go ahead and draw the Venn diagram given on page 244 of our textbook. So, let's say we have a sample space. We'll call it S. S for the normal sample space, right? And let's say the sample space S contains the outcomes 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So, we have two possible groups here. Event E might have the outcomes, for example, 1 and 2, 0, 1, and 2, and event F might have the outcomes 8 and 9. And then the rest of the events that are left over, 3, 4, 5, 6, and 7, are all still inside the possible events, but they're not part of these two. These two share nothing in common. They are disjoint events. So this event separate from the other events. Now let's first take a look at the addition rule right below. So the addition rule for disjoint events. If E and F are disjoint, so they have nothing in common, or mutually exclusive, then we know that the probability of seeing event E or seeing event F happen is going to be the probability of E plus the probability of seeing event F. So let's view that with their example right up above here. I'm going to go ahead and erase this. If I wanted to find the probability of event E happening, well, that's the number of event E divided by the number in the sample size. And the sample size was 10. 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So sample size, was 10. And then items in E are 3. So that would be 0.3. Then the probability of seeing F occur is going to be the number in event F divided by the total items. Number in event F, that's just 2. 2 divided by 10, 0.2. So, if we wanted to figure out what the probability of E or F would be, that would be E or F. How many options? We have 1, 2, 3, 4, 5. That's the number of E or F divided by total sample space. So we said that was 5 divided by 10, which is 0.5. This is the exact same thing as if we had just added up these two values here. Probability of E plus the probability of F. Would it give me 0.3 plus 0.2, which would give me the 5. So these two are the same. They would give us the same outcome. That is if we have events that are disjoint. Keep that in mind. Let's take a look at example 2, Benford's law and the addition rule for disjoint events. Our number system consists of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Because we do not write numbers such as 12 as 0, 1, 2, the first significant digit in any number must be one of the following. We may think that each digit appears with equal frequency, which is what I would think, so that each digit had a 9th probability of being first, or being the first significant digit. But this is not true. Interesting, huh? In 1881, Simon Newcomb discovered that the digits do not occur with equal frequency. The physicist Frank Benford discovered the same result in 1938. After studying lots and lots of data, he assigned probabilities of occurrence for each of the first digits, as shown in our table below. The probability model is now known as Benford's law, and plays a major role in identifying fraudulent data on tax returns and accounting books. That is interesting. Alright, so let's take a look at our data here. Verify that Benford's law is a probability model. Well, what were the rules again? Each of the items had to be between 0, so the probabilities, and 1. So let's check. Yes, yes, yeah. Okay, they're all between 0 and 1. That's good. What was the other thing we had to check? Oh yeah, if we add them all up, they should all come out to equal 1. So let's check that. Add up all those probabilities. Adding them all up, we find out that they do equal 1. Awesome. Check. Alright, so now we're going to use Benford's law to determine the probability that a randomly selected first digit is 1 or 2. So we want the probability of picking, or the probability first digit is 1, or first digit is 2. So this is an OR. And let's real quick check, are these disjoint events? Yes, they are disjoint events. Each one would be different. 1 and 2. So we can go ahead and write this out as the probability of first digit is 1 plus the probability that the first digit is a 2. So what are those probabilities? Probability that your first digit is a 1 is 0.301. Add to that the probability that the first digit is a 2, which is 0.176. Okay, we can add those up and we find out that that probability is 0.477. That's our probability of randomly selecting, randomly selected first digit is 1 or 2. Now let's use Benford's law to determine the probability that a randomly selected first digit is at least a 6. Ooh, here we have that phrase, at least. That means it needs to be greater than or equal to 6. So the probability of at least 6, that would be the probability of, let's see, what are the options we have? 6, 7, 8, and 9. Those are the options. So the probability of a 6, or 7, or 8, or 9. And once again, these are disjoint events, so we can go ahead, break them up. Oops, probability 7, probability of picking an 8, plus the probability of picking a 9. And those probabilities, for 6, it's 0.067. Probability 7, 0.058. Probability of an 8, 0.051. Probability of a 9, 0.046. Okay, adding up all those probabilities, we would get 0.222. So what would these mean in terms of interpretation? Well, let me write these out for interpretation. We'll change from being a decimal to a fraction. So put that all over 1,000 to get rid of the decimals. So this is saying that, and you could go ahead and put it over 100 or something, but this is saying 477 out of 1,000 numbers. So if we looked at 477 out of 1,000 numbers, we would expect them to begin with a 1 or a 2. Or you could say, if we picked 1,000 numbers, we would expect 477 of them to be a 1 or a 2. So if we looked at the next one, what would our interpretation be for this? Well, I'm going to go ahead and I'll write that to get rid of the to get rid of the decimals. So 22 out of 100. So if we looked at 1,000 1,000 numbers, we would expect 222 of them to be at least 6. Interesting. Alright, now let's take a look at example 3. Suppose that a single card is selected from a standard 52 card deck, such as shown below. I always forget how many cards are in a deck. For some reason that number does not stick in my brain. Alright. And let's see, what are we asked to do? Compute the probability of the event of drawing a king. Okay, so the probability of drawing E, well, that's going to be the number of times we see E, the probability, or the event, divided by the number in the total sample set. Well, the probability of drawing a king, how many king options are there? We have 1, 2, 3, 4 options to draw a king. And then how many total options do we have? 52, because there's 52 cards. And that simplifies out to a third. Let's look at the next one. Compute the probability of event E, or event F, or event G, where E is drawing a king, F is drawing a queen, and G is drawing a jack. So we want the probability of E, or F, or G. So I see all the ors, so I know I'm going to use that addition thing as long as these are disjoint, and they are disjoint probabilities. So let's go ahead and rewrite this as P, probability of E, plus the probability of F, plus the probability of G. And what is the probability of drawing a king? Well, we already found that. That's a 13th. Plus the probability of F. What is the probability of drawing a queen? Let's do that on the side here. Probability of drawing a queen. Well, how many queens do we have? 4 queens. Alright. So that will be our number of finding, let's see, number of F divided by number in the sample size. And then we have 52 and 4. So once again, we get a 13th. Now let's go ahead and do that for jack. How many jacks do we see? I see 4. So the probability of the jacks, that's going to be number of jacks divided by number in the sample set, which is going to be 4 divided by 52. Once again, a 13th. So we get a 13th every time, which comes out to being 3/13. And that is the probability of drawing a king, a queen, or a jack. You can do a fun party game with that. Alright. Use the general addition rule. So here's a question. What do we do when we need to compute the probability of two events that are not disjoint? So before, we were just knowing they're all disjoints. We just add up all their probabilities and have fun with that. But now, not all probabilities or not all events are actually disjoint. So let's take a look at a new sample set. S is the whole thing, and then, let's see, S contains, let me write this up here, 1, 2, 0, 3, 4, 5, 6, 7, 8, and 9 as before. And then we have, let's see, some events happening outside, and then we have our two events, but, Hambalala, they're overlapping. Okay. So event, we'll call this one E, is overlapping with event F. This time it's different. They share events in common. So let's say 1 and 3 is what they share in common. And then 5, 7, and 9 E has, and 0, 2, and 4 is what F has. So this time we have a problem. They share events in common. So if we were to just try to find the probability of having E or F just by counting it, we get the number of E or F divided by the number in the whole set. Whole set of numbers, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again. And then having E or F, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 10, which is 4/5. So if we tried to use the addition rule for these, or for disjoint events, so let's say we tried to break it up like we did previously, probability E plus the probability of F. Let's see, the probability of E would be 1, 2, 3, 4, 5 items out of 10, plus the probability of F, which would be 5 items out of 10. And that would be 1, which is incorrect. Okay? Because we forgot, we have accidentally double counted the 1 and the 3. Okay, so the probability addition rule for disjoint events does not work when the events are not disjoint. So we have to find a way to deal with events that have things in common. So the general addition rule for any events, now this applies for disjoint events as well. So it applies for both disjoint and not disjoint. Probability of E or F is the probability of E plus the probability of F, subtracting the probability of E and F, which is what they share in common. So let's retry this problem with the new rule. And I'll go ahead and use it in red. Well, the probability of E or F, if we did the probability of E plus the probability of F, and then we subtracted the probability of E and F, what would we get? I'm running out of room here. The probability of E is 5/10, plus the probability of F, also 5/10. But this time we subtract what they have in common, E and F. So that's 1 and 3, so 2 out of 10. And that would give us, let's see, 8 out of 10, which simplifies into the 4 out of 5, which we had found previously. So that method does work. Alright, so be careful if you have disjoint events. A lot of times it's easier to just use the general addition rule in case the events may actually not be disjoint. Now for example 5. Suppose a single card is selected from a standard 52 card deck. Compute the probability of the event E, drawing a king, or the event F, drawing a diamond. Okay, so what we want is the probability of E or F, and now we need to ask ourselves, are these guys disjoint? Let's take a look back up here at our sample card deck. Well, the probability of drawing a king, we have a 4, and then the probability of drawing diamond is here. Oh no, look at that. They overlap. These events are not disjoint. Darn. Okay, so we're going to have to use the new rule. Let's see. The probability of E drawing a king was 4 out of 52. And the probability of F, which is drawing a diamond, is, let's see how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards. 13 out of 52. Let's write that down. This will be, okay, well we know probability of E was 4 over 52, and the probability of F was 13 over 52. So now, for the general addition rule, we take the two probabilities, add them together, and then subtract if they have anything in common. E and F. Okay, so, well, we found probability of E and probability of F, but we didn't actually find the probability of what they have in common. So let's go back and do that. What do they share in common? Well, they only share one item in common, and that is the King of Diamonds. So that's just one card out of the 52 that they share in common. Which means that probability of E and F is just 1 out of 52. Okay, I'll plug these probabilities in. So probability of E is going to be 4 over 52. Probability of F will be 13 over 52. And the probability of E and F will be 1 over 52. And then we'll get 16 over 52, which simplifies to 4 over 13. And there we go, we found the probability of selecting a card from the deck that is either a king or a diamond. Example 6. Use the data in the table provided to answer the following questions. Part A. Determine the probability that a randomly selected U.S. resident is 15 years old or older is a male. Okay, so we want to figure out... So we're going to say let E equal probability. Let's see, resident is male. So to find the probability of E, we're going to find the number of that event divided by the total number of possibilities. So what is the total possibilities? Well, to find the total possibilities, we're going to add up all these values, those ones and those ones together, and we get 251.3. And now we need to add up the total number of males. So the total number of males would end up being 122.5. Simplifying that, we get 0.487. So that's the probability that a randomly selected U.S. citizen is male. Now, we're going to determine the probability that a randomly selected U.S. citizen, or resident, 15 years and older, is widowed. Okay. Well, let's see. We're going to I'll pick a new one. Let F equal resident is widowed. Which means we're looking for the number of widowed folks divided by the total number of our sample space. And we already found the number for our sample space previously, which was 251.3. So now to find the number of people widowed, we're going to add up the widowed numbers. We have 64.4 and 63.1. So adding those up, we end up with 14.3. And that gives me 0.057. So, if we picked people, probability that they are widowed is 0.057. Now let's take a look at the next option. Determine the probability that a randomly selected U.S. resident 15 years or older is widowed, or divorced. So, we have two options here. So I'll let F equal widowed and D equal divorced. Or actually I should say resident. Resident is widowed. And then we have, I said D is resident is divorce. So we are looking for the probability of D, or F or D. Now, the question is, are these disjoint or not? Well, taking a look at our probability chart, these guys are listed separately. So they are disjoint, which means we can use the regular addition rule for disjoint events, plus the probability of D. If you weren't certain and went ahead and did the subtraction, you would just end up subtracting nothing, so that's okay. Let's see. probability of being widowed is, well, we're going to have to go up and add these guys together to get the probability of being widowed. And then divide that by the total number. So the probability of being widowed is 14.3, which we actually already found up there. 51.3 plus, and the probability of being divorced is 11 plus 14.4, which is going to be 25.4, divided by 251.3. So notice I skipped a small step here. I didn't write that intermittent step there, and that's okay if you skip that step. So adding them up, they have the same denominator. We have 39.7 divided by 251.3. That comes out to be 0.158. So that is the probability of being widowed or divorced and a U.S. citizen. So now let's determine the probability that a randomly selected resident 15 years or older is a male or widowed. So we have two events again. I have a new event, which is male. So I'll say what should we name this one? M. Why not? Let M be a resident is male. And where I already said that F was resident is widowed. I don't know why I didn't choose W there. I will next time. F is resident is widowed. Always let your reader know what your variables stand for. And what we want to find is the probability of M or F. So the question is, do I use this formula? Probability of M and F. Or can I just use the nice simple formula? Which one do I use? The answer lies in the question of whether these are disjoint or not. If they're disjoint, we can use this. If they are not disjoint, we need to use this formula. So let's take a look at our chart to determine which formula we need to use. Okay. Do they have any events in common? So this is male, and we said we're looking for the person is widowed. Oh, look at that. They do have a common thing right there. That's their commonality. Let me redraw this a little better. There we go. They have a commonality which is 3.1. So because they are not disjoint, we're going to have to use this formula. So what is the probability of being a male? Well, that's going to be... Actually, you know what? I already used that probability. I said E. Darn, let me change this here. I'm using the wrong variable. Too bad I didn't think of this sooner. We are already using E. And we found that probability at the very first question, which was, I'll just go ahead and go with 0.487. Plus the probability of F, which is person being widowed, which we already found here, 0.057. Now we need to take away the probability of them being widowed and male. So the probability of being widowed and male is 3.1. Out of the 251.3. Notice we already did that for these values, so we have to do that for our last one here. And then subtracting away and adding with our calculators, we'll get 0.532. Alright, a little tricky, but you can keep things organized. Alright, objective 3. Compute the probability of an event using the complement rule. Okay, so a slightly different way of computing the probability. So, definition for the complement of an event. Let S denote the sample space of a probability experiment, and let E denote an event. The complement of E denoted E complement is all the outcomes in the sample space S that are not the outcomes in event E. For example, if E was having an even number on a die, then the complement of E would be all of the odd numbers. Now let's take a look at the complement rule. Well, the complement rule is if E represents any event and E complement represents the complement of E, then the probability of E complement is just 1 minus the probability of E. Let's take a look at example 7. According to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? All right. Well, let's let E equal American has not played the lottery. So how do we find that? Well, the probability of E, I have the complement going on. I'm trying to find out how many have not, and they give me the probability of those who have. So let's use the complement rule here. This would be the same as 1 minus the probability of those Americans has played lottery. And we know that probability. The probability of Americans who have played the lottery is 52, or 0.2. Sorry, 0.52. So doing this subtraction, we get 0.48 is the probability of Americans that have not played the state lottery. Or state lotteries. Let's take a look at example 8. The data in the table below represent the income distribution of households in the United States in 2013. Compute the probability that a randomly selected household earned the following incomes in 2013. 2,000 or more. Alright, let's see. Let E equal earning 2,000 or more. So the probability that someone earned 2,000 or more is going to be the number of people that earned 2,000 or more, divided by the number in the total sample space. So, who has more than 200,000? Well, just these guys earned 200,000 or more. So 5,913. And then we have to divide by the total in our sample space, which would be adding up all of these values to find the total sample space for right here. Okay, well, what do we get? When I add all of those up, we get 122,953. Okay, plug that into a calculator and we come out with 0.048. That is the probability of randomly selecting a person who earns 200,000 or more. And notice, this is below 5%, which we said was the unusual threshold. And that would make sense. It's unusual to find somebody that earns that much money. Or randomly pick them off the street and ask them how much they earn. All right. B, the probability the person earns less than 200,000. So I'll say let E equal person earns less than 200,000. Okay, so we have the probability of E equals, well, I could go through and compute all of these probabilities for each grouping and add them together to find those that earn less than 200,000. But that would take a lot of time. So because I don't want to do that, I can actually use the complement rule. So the probability of this would be 1 minus the probability of E complement. So what is E complement? E complement is person earns more than $200,000. And we found that probability. That one was right up here. So we have 1 minus the complement. And we can get our probability of 0.952. Okay, so why did I decide to use the complement rule instead of going through and adding up all of the probabilities? It would have just taken a lot more work. I would have to have taken this number, divide it by the total, which is the 122,953. Then I would add that probability to that number, divided by this. Add it to that number, divided by this, and so on. That would take a lot of time. So if you can use the complement, a lot of times it will cut down on your work. Alright, so, next one. The probability the person earned at least $10,000. Okay, so let's let M equal person earns at least $10,000. So what would this be? Well, to compute that, let's look at our chart. Because I want to find out the people who earn at least $10,000, that would be computing the probabilities for all of these categories. So once again, I would have to take this number, divide it by our total, add that to the next number divided by our total to find the probabilities for each of the categories. That is a ton of work. Is there another way I could do it? And the answer is yes, I could use the complement. So what I can do is I can say the probability of M is going to be 1 minus the probability of M complement. And what is M complement? What's the opposite of a person earning at least $10,000? That would be a person earning less than $10,000. So M complement is person earns less than $10,000. So let's find that probability. Is that easier? Let's see. Well, yeah, there's only one number group for the people who earn less than $10,000. So we'll take the 8,940 and divide that by the total number from all of these. Let's see. 8,940 divided by 122,953. Plugging that into our calculator, we'll get 0.927. Okay, so the complement rule does come in handy. If you find out that you're going to have to be finding out the probabilities for more, and I would say like if it's more than half of the data, then I would start thinking of using the complement rule. Alright, so please email me if you have any questions.